Hello, everybody. So, yes, this will be a talk a lot about linked data, about knowledge on the web, especially common sense knowledge. But I will also end up with some more general remarks on semantics, so I hope you'll find this interesting. So, many of us are interested in knowledge, some of us in common sense knowledge, and one of the places where we can find a lot of this knowledge is on the web. And some of this knowledge is facts, assertions about things. This is the first thing that usually comes to mind. But a large amount of knowledge is about activities, how to do things. So many times you've probably been on the web and looking for the solution to a problem, how to do something. Maybe some of you even have created such knowledge on the web. And this is a very important kind of knowledge, but in the common sense knowledge field, in the linked data field, has been a bit overlooked. So I will start by saying what I did to integrate this knowledge in the linked data cloud and make sure that there is a way for machines to actually understand this knowledge and use it. So, well, as I said, we all know there's a lot of knowledge on the web, a lot of documents, and about know-how. Maybe some of you have looked at this website, WikiHow. Probably have already seen that. There are a lot of instructions on how to do things, some a bit strange, but in general it's a good thing. There's a lot of variety there, a lot of content. They're very large knowledge bases. Very similar to Wikipedia, but they deal with procedural knowledge on how to do things. So why artificial agents cannot understand this knowledge? Well, we know it's because many of these documents are intended for human readers. So they're generally unstructured, like a simple HTML page. So if we want to make use of this knowledge, we have to find ways to make it machine understandable. And so in order to take this knowledge and integrate in the linked data cloud, there are some steps that one could follow. There are many aspects to this, but these are a number of things that I think are very important. So first, one would start with unstructured knowledge, unstructured documents found on the web, which contain knowledge, which is not accessible easily by artificial agents yet. Then this knowledge can be transformed in a structured format. In the context of linked data, this usually means RDF. Then this knowledge is interlinked with other documents to provide context and more information about, for example, how to do something or about what a particular entity is. And finally, when we have that, we can reuse this knowledge in a way that was not possible before, in the same way as we can use knowledge from Wikipedia, thanks to DBpedia, to do things that are not possible, well, not easily, just by looking at Wikipedia pages. So the first step, as I said, is transforming unstructured documents into data. And to give you an example how the system I created works, how this works, we can see an HTML page, well, a representation of one, on the left, and on the right we see a graph that represents the various entities and the various relations between the various parts of this set of instructions. So this is instructions on how to make a pancake, and you can see, you can distinguish steps, an order in between the steps, maybe some requirements, and this gives structure to this set of instructions and makes a lot of the relation of the entities that you can find in the set of instruction explicit, so that artificial agents know about these things. So I performed this extraction over WikiHow and SnapGuide, obtaining over 200,000 procedures. And as you've seen before, they get decomposed into various entities, and altogether was over 2.5 million entities, covering a lot of human know-how. So this is a fairly big knowledge base. So if any of you is interested in common sense reasoning and want some data about human activities, I'm very happy to share this data set. But this is not the end of it, because we've seen the data, but it's not linked yet. So to make it even better, we can create links between the various entities. And I've especially looked at two different kinds of links. One is a functional type of link. So we can see here, if you're looking at instructions on how to install an operating system, maybe one of the steps requires you to create a partition. And if you don't know well how to do it, or if a machine wants to anticipate your needs on what you might do next, it's very useful to know that there is a connection between this step and a set of instructions on how to create a partition, which maybe another document describes in more detail. So this is one kind of link. Another kind of link is obtained by disambiguating entities with an external knowledge base. So we can see here the input and output of two processes is disambiguated with dbpedia. In this case, guacamole is the input of one process and the output of the other. And by knowing that these two entities are of the same type, we can infer an input-output link between the two processes. So we created this new link now, exploiting this external knowledge base. And finally, when we have this, we can reuse it for many different things. So this structure that we have created, these new links, can be used immediately by humans to maybe visualize and explore this data better, or it can be used by machines to do further processing. For example, this is an application that we developed actually in Japan during an internship, and this is this shows you data from WikiHow and SnapGuide and dbpedia all together in just a single visualization. So you can look at steps, requirements of processes, and you can find pictures from the web. And we can see here there's an extra box on how to make coffee, and if the user clicks on that, we'll see more information on steps that are usually required to make coffee. But how to actually evaluate the links that we have created between different sets of instructions? Well, we have evaluated this against human-generated links, actually community-generated links. So if you've been to WikiHow, you might have noticed sometimes links between different pages. These are exactly the same kind of links that I showed you before. So between steps and other processes, or between objects and items that are required by a process to other documents. So we have taken all of those generated by humans, and we have compared them with the automatically generated links. And the outcome was surprisingly good. We got many more links, better coverage, so many more sets of instructions had at least one link. This is what coverage is about. And we even got more precision than the human-generated links. Now, this might sound a bit surprising. It has to do with how links are actually generated within the WikiHow community. I can discuss this a bit later if you're interested. But in general, it was a clear improvement, and this was thanks to exploiting linked data, external knowledge bases, and creating these links automatically by having machines understand the various entities that a process is made of. So if you're interested in this, and this is the website of the project, and again, you can contact me if you want to use this data. So this was about a year ago, and after this, I expanded the project in many directions, and I wanted to talk a bit about something that came up as a spin-off of this project. Something that you might be interested in is a bit more generic about semantics. So as I was working on the definition of abstractions for processes, so for example, a common entity that would describe a lot of recipe, let's say that a lot of different variations of recipes. I don't know how to make a specific kind of dessert, for example, distinguishing the abstract task from the specific variants. As I was working on that, I stumbled on this thing that I think is an important challenge for linked data, and I wanted to say a couple of things about this. So this is how I phrased it. The more a concept gets reused, the least semantically rich it becomes. And semantically rich here means how many facts we can infer about a concept, about an entity if we know it's a member of a concept. And basically, if we reuse a concept frequently, and here I mean linked data concept in an open environment such as the web, it will gradually lose its meaning. And this is a challenge because linked data is based on sharing semantics and assumes that you can reuse the same concept, URI, the same relations with the same meaning all across the web, and they should always carry the same meaning in theory. But we already know this doesn't happen. So, for example, there has been work showing that same as has been abused, let's say, in the sense not used according to the original meaning. And Emilius yesterday was mentioning also this. So, for example, Edinburgh, you can find that Edinburgh, the URI for Edinburgh can be asserted to be equal to maybe a picture of Edinburgh, or the location where it is on a map. Well, clearly these are similar things, but not exactly the same. So Edinburgh is not a picture, or this picture does not have a population of 500,000. These are all wrong inferences that come up because this relation is used in the wrong way. And I investigated this a bit more, not about relations, but about concepts. So in the semantic web, what is a cat? So imagine you find an entity and you know it's a cat. What do you know about this entity? Well, if you're in a very specific domain, you might infer a lot of things. So maybe originally this was the meaning of cat. And the person who defined this ontological term had this in mind. So if you know something is a cat, you can infer a lot of things. It has eyes, ears, a tail. But maybe somebody else later decides to reuse this concept and says that this is also a cat. And some would agree, but you can already start seeing is something a bit different. This is a fictional cat. Then somebody else can reuse this concept and say that this is a cat. And this is not even a living being. Or maybe this is a cat. Well, maybe it's more like a t-shirt. Or why not? This could also be a cat on the semantic web. Basically, since anybody can say anything about anything, anything can be a cat in the semantic web, basically. So in order to measure how much of a problem this actually is, I defined a measure of semantic richness that is based on how many patterns entities of a certain class have. So for example, if we know that entities of type cat, all of them are mammals, almost all of them have a tail, then we know things. We can infer things by the fact that we know that something is a cat. So these are these patterns that we can find, those increase the semantic richness of the concept of cat. But if we don't have, if there's nothing we know, then the semantic richness will be very low. So I created a simple measure that can be evaluated on any linked data set automatically. And to validate it, I applied it to the DBPD ontology. So here you see the DBPD ontology tree from its root, basically all thing, the most generic concept, the least semantically rich, down into the hierarchy level to more specific concepts like person, engineer, mechanical engineer, and this. And as you can expect, the semantic richness measure shows that more specific concepts are in general more semantically rich, which is what one would expect. It is not always the case, and this has something to do with how the DBP ontology is and the fact that sub-concepts are mutually exclusive, but this is a separate issue. If you're interested, you can ask me later. And to evaluate if the semantic richness actually decreases, I looked at the fourth person concept, from 10 different databases on the web. And I've evaluated the semantic richness of this concept within each of these data sets. And then I started adding to these data sets more and more entities taken from other data sets to see how much the semantic richness would change. And this is the result I get. So you can see that the semantic richness decreases quite quickly as you add more entities. I should add that the data set was, each of these data sets was a subset of 1,000 entities taken from the original data set. So this is why when we reach about 1,000 new random entities added, the semantic richness is very low. And actually this dotted line shows the average semantic richness of all the original data sets. So if you knew which data set a certain entity of type person comes from, there are some things that you could infer about that. So the semantic richness would be higher. But if you don't know this and you put all the entities together, if you just pick a random entity and you know that it's a person, there's very little that you can know if you put them all together. So this is how I evaluate this empirically, but according to the measure, it can also be shown mathematically that semantic richness can only decrease or remain equal. So to conclude, I start talking about common sense know-how on the web, telling you how this knowledge can be found on the web, it can be made into linked data, can be linked with each other and with external knowledge bases. So basically adding a new dimension to common sense knowledge on the web, which was mostly about facts, like DBpedia, and not much about how to do things. But this knowledge is very important for many applications, so, and it can also be extracted in a similar way. And finally, I concluded with this issue about linked data, and this thing that I think it's an important challenge, and some of my investigations about it. Yep. Cool. Mm-hmm. Mm-hmm.
This means we don't really lose any semantic richness if words become more ambiguous, because we use them in a particular context, or we apply some default to the reasoning which is appropriate in a certain context. So it doesn't really mean that, in my view, that they are becoming less rich. It simply means that you need the right kind of logic, the right kind of reasoning mechanism in order to talk about this.
So yes, within a specific context, there are, if you know the context and you apply some specific rules, then yes, you can preserve more knowledge about the concept. But to explain a little bit how I calculated this, is it doesn't presuppose any inferent rules, because actually many linked data sets on the web don't have that. Basically, the way it calculates it is with inductive learning. So how many things we can infer from a set of items. So it's based on that. So based on inductive learning, if you add more and more entities which have different patterns, have different properties, then the things you can infer about a specific entity are always decreasing. So it's more about inductive learning than a proper ontology with rules. Yeah.
So it's more like an information
Yes, it's very similar to the information content metric for information theory, but it's different. Like, for example, you couldn't apply the information content metric on these data sets because of the way it's defined. And if you only have, for example, a data set with only one type of concept, entities of one type, then you cannot apply information content, it won't be meaningful. This is why I adopted this inductive learning approach. Mm-hmm. Sorry?
What you call it richness, for me, is lack of richness. So, for me, person is a rich concept, in the sense that can be used in many ways, in different roles, in many contexts.
The set of entities increases, yeah.
Because of that. So, the opposite would be something more specific. Imagine something very, very specific, of which I can infer just one thing. According to your definition, that would be rich. For me, this is, let's say,
So a very a very specific concept would have usually less entities. So, for example, mechanical engineer is very specific and more semantically rich because you can expect, let's say, from a mechanical engineer to know more things, well, more specific things than from an engineer or from a person. So that is why it's more semantically rich and also more specific. But of course, the set of entities reduces. So if you use the term mechanical engineer for every person, then if you know that somebody is a mechanical engineer, you cannot assume they have certain skills. This is the root of the problem. Yeah, the meaning gets diluted. Maybe it's the way it's phrased. Yeah.
So I have a question that is kind of related. So especially I mean, you said what you're doing is for artificial agents.
Yes.
Yes. So I think that the issues that were raised or the other questions are to do with how it would be used, how this knowledge would be used.
Yes, it's.
And for example, in the human-computer interaction literature, there's a long-standing debate about whether plans, for example, in the AI sense, are actually useful for people.
Mm-hmm.
Whether actually people ever do things the way the plan says it,
Mm-hmm.
or whether plans are rather resourced, and there's lots more things going on, or variation, and ambiguity, and these ambiguities and so on are good.
Mm-hmm.
So I was wondering, I mean, do you personally think that this could be like, let's say, that cooking recipes, brick perfumers, could actually be really reliably and robustly used by, let's say, a robot?
Well, there is actually a research project that did exactly that. So they took a robot and they asked him to do a pancake, and without telling him, without telling it how to do it, and it basically had to go online, parse WikiHow instructions, and do it. Now that wasn't a 100% success, but still it could reuse a lot of information from WikiHow and other knowledge bases to infer some things that the authors of the experiment didn't have to write down explicitly. But I want to mention that this is not ultimately to have robots, well, it's not now just to have robots complete these tasks. There are a lot of things that artificial agents can do, even just pointing you to the right information or displaying in the right way, or making some clever inference by knowing that you will probably need a certain item because as you're doing a step, it will probably require doing something else. So that's why I haven't looked at actually automatically doing these things, but other applications like visualization and linking to, as a use case.
So I think these use cases will give a better handle on what richness is, or kind of coming back from a task and saying, how does usefulness map to richness, and then
Mm-hmm.
with an idea of a certain inference
yes, it's ultimately the more semantic rich something is, the more inferences you are supposed to be able to make. Yeah.
Okay, then let's thank Paolo again.
Okay.